Okay, so this is supposed to be a discussion of open problems in quantum gravity. So I'll write down some questions on the board, and all of you can answer them. There are, of course, a lot of open problems in quantum gravity, and that's good. It keeps us busy. But here are some of my favorites. So one, what is a quantum black hole? We talk about quantum black holes all the time, but I want to know what it is, not semi-classically, but in full quantum gravity. So in a holographic description, this is like finite n. Now, most discussions of the subject starts by drawing a Penrose diagram. So in ADS, people will often, draw a two-sided black hole like this, or an evaporating black hole like this. But these are certainly classical. They are, in fact, probably not even correct classically. It's known in asymptotically flat space-time that generic black holes don't look like this. The singularity inside a black hole starts off null. So in ADS, it's not been shown that the same thing is true. I'm talking, of course, about rotating black holes, which, of course, are the generic type. You need fine-tuning to keep the black hole 0, or in a quantum theory, it would only be the J equals 0 eigenstate of black holes. That might have something to do with this. But any non-zero angular momentum, we know that the singularity is null. So maybe, of course, it might, don't quite know whether it stays null or whatever, but it certainly should start null, something more like this. Okay, so these diagrams give the wrong answer for many of the questions. We know they're the wrong answer. These types of spacetimes would predict a continuous spectrum of states. There's an infinite redshift near the horizon. So you can add arbitrarily small energy. We know from ADS-CFT, a finite n gauge theory on a compact boundary must have a discrete set of states. It also predicts that the two-point function decays exponentially for all time. We know that also isn't correct by looking at the dual field theory. Okay, so these diagrams are sort of giving us the wrong answer. And the question is, what is the right description of a quantum black hole? Clearly, it has to have a horizon. But another way to ask the question is, what is a quantum horizon? What does that mean? I mean, a horizon we think of as something which distinguishes points that are causally separated from asymptotic observers. But to define causal relations like that, you need to know the space-time everywhere. And clearly, any notion of our space-time is going to be breaking down near the singularity. People have suggested a better picture for a space-time. You could have something like this, some region of quantum gravity where the metric is clearly ill-defined. There's some boundary here, maybe. But, why couldn't this be as good a picture of a black hole as something like that?
Yeah. Picture, there's no horizon?
Well, that's the question. What do we mean by a horizon? This is a space-time saying clearly our notion of a metric is going to break down near the singularity. So let's put that in. But, why should the space-time begin here and not here? I mean, it's not clear.
Fuzzball would be an example of that, or something another.
Oh, a fuzzball. Okay, now let's see. Nick Warner was telling me the difference between
it doesn't have a horizon.
Fuzzballs and so fuzzballs don't have horizons,
but
microstate geometries would just be classical solutions.
They have classical geometries, but no horizon.
Classical geometry, certainly all this, all the things that Nick Warner and people have been.
There's a distinction between a microstate geometry, which is something with pure geometry, and a fuzzball, which is some quantum state within that system, within such a system. So there's a lexicon here, but there's no horizon in those.
Certainly fuzzballs would not have horizons.
I'm just going to make a very small comment. You talked about the two-point function, the fact that it should not decay for all time.
Right.
That seems to indicate that there's no such thing such as a quantum horizon.
Great. Well, I mean, maybe the answer is there is no such thing as a quantum black hole, and we should stop calling it that. I mean, that is a very possible resolution here.
But then what does LIGO see?
LIGO
Look like black holes.
Whatever they see, that's what we should call black hole.
They're seeing.
Doesn't everybody agree that outside the black hole, we all know what we're talking about? Sufficiently outside the black hole.
Yes, I mean, most people will agree that outside the black hole, when the geometry is sufficiently classical, we should get something like the standard GR answer.
Which is what LIGO sees.
Which is certainly what LIGO sees. Everything LIGO sees is consistent with classical black holes. But as a classic, I mean, LIGO can all be analyzed and has been analyzed using classical relativity. The point here is to understand what, this is supposed to be quantum gravity, and what is a quantum black hole? Steve?
Well, so why isn't a reasonable answer something like there may not be any fundamental quantum horizon, but there are things that effectively look like horizons in the case of big black holes, etc.
And what does that mean, effectively look like horizons?
Well, something, for example, if you have a region of space-time that is behaving semi-classically with something like trapped surfaces or what have you, the light rays going inward, etc. So, locally it looks like you have a horizon structure. That's just an approximation, right? It's a good approximation for big black holes. That's all it is an approximation.
I mean, Neda?
Well, it seems to me that defining a black hole in terms of a horizon is a very classical thing to do.
Exactly.
So I don't think we should be looking for something like quantum horizon, because I don't think that that's an intuition that we should be applying to quantum black holes.
Well,
It's somewhat similar to asking what is a particle. Only, to be strict, only the electron, positron, photons, graviton are particles. But we talk about particles all the time. There's a parametric sense in the standard model and filter allows us to say the proton is a particle.
Okay.
Now, it isn't. Neutron is certainly not a particle. And there are parameters in our theory that allow us to understand that.
There's no doubt that there are limits, there are sort of reasons where it's reasonable to take the sort of standard black hole picture, seriously. But I now want to ask the question, what is it really? I mean, in the full quantum theory, what is the object that these are approximations to?
I have no proposal for what it is, but I'd like to make a comment, which is that normally we think of, in our language, we talk about the black hole as a state in the quantum theory, but black hole is a space-time, so it's a state with a particular evolution. Okay. So, for example, we can take the thermofield double state, and if we evolve it with different Hamiltonian, let's say a coupled Hamiltonian, then there might be no horizon. If we evolve it with the decoupled Hamiltonian, then there is a horizon. Mm-hmm. So it's a proper not only of a state, but also of a state together with the evolution.
Good. Actually, that touches on something I was going to say in a minute, but let me...
one comment. The definition of a black hole we've had for about 200 years. The idea is it's something that traps light. Now, you can do what Mitchell did and answer Newtonian gravity and corpuscles. You answer it in GR, you get this. If you answer it from the perspective of fuzzballs, you can trap light for arbitrarily long periods of time with a dense random medium. So the answer of what a black hole is, the best definition I think is the operational one. What traps light for arbitrarily long periods of time in some limit, and then you answer that within the framework of the physical theory you bring to bear. If you use Newtonian gravity, you get one picture. If you use GR, you get another, and if you use string theory, I think you get a third one. Possible.
Okay. Okay, Aaron?
Yeah, well, doesn't the sun trap light for millions of years or something? There's a sort of a horizon in the bottom picture we drew here.
There is sort of a...
If you've defined what you mean by the quantum gravity region, you can take the boundary of the past domain independence of that, I guess.
Well, yeah, I mean,
Draw a line like that.
you might think, okay, so there's sort of a horizon here because then to get out to infinity you have to go through this quantum gravity region and who knows what happens. But the whole point of this discussion is I'd like to imagine we have a quantum theory of gravity which knows what's happening in here. If there's some state, it's going to evolve the state. It's
but
just
what
because
this picture is depends a lot on what you say this dashed line is doing. The question is, does the dashed line have small area by the time you reach the quantum gravity region, as in the standard picture, or does it still have big area, as in maybe the firewall fuzzball picture? Those
Okay.
are two very different.
They are different
It's not
things.
the same diagram, but they're two very different hypotheses.
okay, Steve.
Well, so maybe a pre-question for this is, what is a quantum space-time, of course. But let me give you another answer regarding the black hole, and that is you can think of it as a certain kind of resonance or family of resonances in the S matrix.
Good. So that's another. Okay. So let me actually move on because there's people have touched on things I wanted to sort of bring up next. So clearly we want to imagine a black hole as somehow a state which in some sense the geometry looks like this, but there are fluctuations which maybe are small away from the black hole and maybe get big inside or something. But what do we mean by fluctuating light cones and all that stuff? So if we want to go for a purely quantum definition, so here are sort of proposals for a quantum definition. And so let me break it up into two categories. So I first want to think about large black holes in ADS, which don't evaporate. Okay, sort of stable black holes. So large ADS black holes. And so here, I don't know, as it's just learning from everything that you guys have been doing, one might suggest that a black hole is, large ADS black holes sort of are characterized by something like maybe a high energy spectrum, high energy spectrum of the Hamiltonian, which is essentially random eigenvalues. High energy random energy eigenvalues. Something that Steve Schenker keeps drawing on in his discussions. And that probably has to be coupled with some notion of statement about the dynamics, as one was mentioning, something about the dynamics that has fast.
Already the dynamics?
No. Okay, this was actually a question I asked Douglas this morning. You might say, if you know all the eigenvalues of the Hamiltonian, don't you know the Hamiltonian? And Douglas explained no, because you need to know the eigenvectors, and you need to know what operators are of interest, et cetera, and how the Hamiltonian mixes or spreads operators of interest. Okay, so this was the next part, the dynamics that incorporates fast scrambling and maximum chaos. Okay, so scrambling and max chaos. Okay, so these are certainly properties that have been derived by people here that we believe black holes have. So could we define a black hole by this? Could a system with a high energy spectrum, so first it has to have enough high energy, random energy eigenvalues with the density, with density expected, like given by this exponential of the Hawking-Bekenstein entropy.
Maximum chaos is a classical feature rather than quantum feature.
What's that?
Maximum chaos is a classical feature.
Maximum chaos. No, but I'm thinking about these out-of-time ordered correlators of operators, and that, that's a quantum. It's something you can calculate. It's an expectation value of some out-of-time ordered correlator. What's that?
It's calculated by classical GR, right?
It is calculated by classical GR, but it's supposed to be true of the quantum theory. So even away from the classical limit, you might expect that would be a property.
These are all large N.
Yeah, somehow that list isn't good enough by itself, right? Because like SYK satisfies both of those, but like doesn't really have Einstein gravity. You know, it doesn't have a local bulk description.
Well, it has something we might call a black hole, though, right?
I mean, it's kind of not local below the ADS scale, right? So, I mean, yeah, I mean, it depends how you know, I mean, a lump of coal also is kind of like a black hole, right? So,
Okay, well, so the question is...
SYK is a little more like it than the lump of coal because it has number 2, but...
It's been proposed that you just need to make the criterion for number 2 very strong in basically ADS2 cases, and that would rule out SYK. So how close to maximal chaos you need to be might be closer in ADS2 cases than a generic case.
Yeah. So if this is not enough, you know, one could add another property. But, you know, this is maybe, you know, if we want a quantum definition of a black hole, you know, this is the sort of things that maybe we should be thinking about. But as Steve brought up, this is only true for black holes that don't evaporate. And what about the smaller black holes? Okay, so for evaporating black holes, how are we going to define them? Well, as Steve says, they're not energy eigenstates. They're unstable. They all decay. So there's some sort of resonance. But clearly not all resonances should be black holes. So we need more properties. We need something about what makes a resonance a black hole as opposed to just a typical particle decaying. And so these are, yes?
Yeah, well, so there's a certain spectrum, you know, very closely spaced levels, certain characteristic decay times for emission of Hawking radiation.
But spectrum of, I mean, these are not particles. I mean, so they're not.
The number of energy.
So you want to imagine there's still a discrete set of energy eigenstates?
Well, the problem is that the spacing between levels, between the energy eigenstates, is much
smaller than the width. Exactly.
Okay,
so they're not energy.
A high density of states, you might say.
High density. Good. That's certainly, yeah, high density.
It's pretty close to this, but you know, and I think this is a way of isolating what we mean by a black hole in the S matrix. But there still is this question that a black hole is something, you know, we think if it was big enough that there are operators that could see something that looks like an interior space-time that might be perfectly normal-looking space-time for a limited amount of time. And you know, somehow that's not part of either of these definitions, and something you might want to include to make contact with
Right. Okay, Anna?
They should have a page curve. I think it should grow as fast as it can, and then fall down as fast as it can.
Good.
I think that's like saying that they should be fast scramblers or something.
Good. Good. So you have a state in which it sort of decays, but the entropy of the decay products grows, and then it doesn't happen for anything that decays. Anything that's decaying to a lot of particles, the entropy will grow and then go back down
But
again.
it grows as fast as it can, and then falls down as fast as it can. Usually things just follow just some random trajectory like this.
Okay.
But the age curve is where the entropy, well...
I would say if you buy a lump of coal, it goes up and then it goes down.
Yeah, I think anything will do this. Any quantum system will do this, so I'm not sure this is...
No.
I'll put a dash line. Maybe.
I don't think you expect that at early times the radiation for a generic system approaches a maximally mixed state. So if I give you a random state of a set of n qubits, and then I look at a small fraction of these qubits, then if the state was truly random, then that density matrix is arbitrarily close to, or very close to being maximally mixed. For a black hole that's evaporating, you expect that to happen. But for a lump of coal that's burning, I don't think you expect that.
Well, this is a question of how quickly does it thermalize perfectly, right? So if it thermalizes perfect, it's about the thermalization time rather than the scrambling time, right?
Also, if energy is conserved, then it wouldn't have to increase density, would be constrained by conservation of energy.
I think we think that the entropy will be as large as it can be given the coarse-grained conservation laws.
But so H derived his curve from, assuming kind of a random evolution of the quantum system.
Okay, let me move on because there are a couple of other questions I wanted to mention for discussion. So, second question, can one define Euclidean quantum gravity beyond the semi-classical approximation? And maybe I should mention in 4 dimensions.
So, Gary, by Euclidean gravity, you mean just the metric? Is that the variable? Or?
No, you can add matter. So, I mean, basically the question is, do expressions like this, g e to the minus, the action, the Euclidean action, say, the metric, do expressions like that make sense?
But why? We know that they don't make sense.
Yeah, I thought the answer is no.
Higher order terms or arbitrary? What's higher?
Okay, I mean, I'm imagining if string theory involves, excuse me, an integral over metrics as well as all the other stuff, rather than an integral over gauge fields or some completely dual variables, anything which involves functional integrals over metrics plus matter, and this action, it can have higher curvature terms, it could have whatever you want. Arbitrarily higher curvature terms.
So non-local. Non-local.
It can be non-local. Okay. You're just making it harder to define.
Yes, but
yeah.
Possible.
It's possible.
Most likely.
Yeah, but your action is unbounded below.
But you pick some other contour.
That's the question is, can you fix that? So.
You picked some other contour, right?
Well, okay, so that's
the least of your problems.
All right. So that starts off, as you guys are saying, with the, Hawking and Gibbons, started writing down things like this. It was immediately noticed that the Euclidean-Einstein action is not positive definite. You can make it arbitrarily negative. So then they start introducing these other contours. Okay. So the question really is there a contour, is there some way of making sense of expressions like this other than what everyone's been doing, which is looking at the saddle points and maybe small fluctuations around the saddle points and just using that as an approximation for the wave function.
But Gary, here you're imagining like some kind of asymptotic safety. Is that what I can apply to? Can I call a yes answer to this, asymptotic safety?
Well,
it's a different question.
That's
a perturbative question.
I think what Gary's asking is, can you define maybe a contour or something where you could choose, for example, in a situation that you have several saddle points, is it defined in such a way that I could choose a contour?
Yeah, are there rules which...
UV problem, right?
No, it's not the UV, not obviously a UV problem.
They're UV problems and they're just bounded from below problems.
Yeah, these are
R squared would not require any modification.
You can certainly make a positive definite action.
Exactly. So you want something that in some sense contains Einstein gravity.
Yes. I mean, then there's induced gravity that you might, think about.
R squared people have
right.
You're not asking about Lorentzian description.
Well, this was a question about the Euclidean approach to quantum gravity. What's wrong with R squared?
Except for the UV.
The UV is...
Yeah, but that's perturbative. So what's wrong with R squared as an answer?
Oh, I don't want it just perturbative. I want this to be...
R squared looks like it is well defined, right? You must have other requirements to make this interesting.
Right. Well, of course, I want the usual... Okay, I want an Einstein term because, everyone has been deriving or computing saddle points to this thing and then interpreting them.
You can say R plus R squared, that's fine, right?
And then there's questions about...
The IR problem.
There's a deeper issue really with this, or the Lorentzian version. We don't really expect that a manifold with a metric on it makes sense, certainly below the Planck distance. Okay, so that's just not right fundamentally at the level. And then we know that sort of the problems we thought we just had at the Planck distance actually reach out to longer distances when we start encountering very high energy behavior like quantum black holes. So it looks like this.
Okay, so you're arguing no. That you're arguing if the metric is not a fundamental variable in any sense in quantum gravity, this is just not going to make sense. And we shouldn't think of this as a good starting point for quantum gravity.
That's what I think.
Do you think the boundary CFT is a definition?
Okay, so that comes up to my next point.
But that doesn't look like this, right?
Hold on. You know, okay, before we get into this,
This is so general.
I want to read, there's a wonderful quote from Sidney Coleman that some of you may know. This is in a paper that Sidney wrote back in 1988 when he had a paper called Why Is There Nothing Rather Than Something? A Theory of the Cosmological Constant. And it was in the spirit, using these wormholes that Steve and Andy and Sidney have been talking about. And he says, the Euclidean formulation of gravity is not a subject with firm foundations. It is more like a trackless swamp. I think I have threaded my way through it safely, but it's always possible that unknown to myself, I am up to my neck in quicksand and sinking fast. So that was the situation back then. Nowadays, and I have to say, for a long time, I thought we could answer this problem using holography. After all, we have holography, the answer. And so now what is holography? Holography says that if you take a space-time which is asymptotically ADS, it's in the Euclidean thing, then the gravitational partition function, this guy, the full partition function for gravity, with some boundary metric, is supposed to be equal to the partition function for the dual CFT on a space with the same boundary metric. This is certainly well behaved, well defined. And so for a long time I thought if we could just unravel this, we could in fact define the gravitational, the appropriate rules for the gravitational functional integral for gravity. And indeed, back in 2007, there was a paper by Joe and Nima and a student here, Jacopo Orgera, in which they studied gravity in asymptotically ADS space. They found a wormhole. They found one of these Euclidean wormholes, and then they said, even though it's a saddle point of this action, it must not contribute because it would violate rules of the dual CFT. Now, I hear people saying, there are wormhole solutions of gravity, therefore we must modify the CFT, consider ensembles of theories. I mean, I'm getting whiplash. I just don't know what the rules are. And so we need to do something, we need to somehow find out what are the rules. Do all saddle points contribute? Should we throw out some?
We surely don't think all saddle points contribute, right? I mean,
well, Jim Hartle had a nice paper last year in which he talked about his no boundary wave function in terms of the saddle points. And you had a couple of other conditions, right? You required the wave function be normalizable.
Time reversal invariance, that kind of thing.
Right, so that's fluctuations had to be damped.
But even in quantum mechanics, all the saddle points don't contribute, right? Like it's a subtle question about the path integral contour, which ones count and which ones
Right, normally we have a contour and we can ask which ones contribute in a steepest descent way. Yeah. Here we don't start with a contour. So anyway, so that's one of the...
Our point was all our calculations of comparing the predictions of the no boundary wave function to realistic cosmology were all done in the semi-classical approximation. So all we actually need is the wave function defined in the semi-classical limit. That's what we did.
Yeah. So, Aaron?
There's one thing we know for sure, which is that not all CFTs are ensembles of CFTs. So, isn't the answer to your question, to your whiplash, just that it's a big world, and you can consider both CFTs and ensembles of CFTs, and they can both be dual to quantum gravity with somewhat different rules?
No, I don't think that's the answer.
What is an ensemble of CFTs?
Yeah, what is an ensemble of CFTs?
Something like the SYK model, where you are averaging over lots of possible values of the coupling constant that are the same through all space and time in the CFT.
I want to just go back to string theory. This correspondence, right, is not with that integral, but rather with string theory. Right?
Yes, this comes from string theory.
And so it's not really, wormholes are non-perturbative. The correspondence with string theory is perturbative. So that's why we don't know the rules, correct?
Okay, so you're right. Strictly speaking, the holography says that the string theory, full string theory partition function. Now, we usually think of it as including this, but maybe that's wrong. Maybe we shouldn't actually.
String theory, so that is an attempt in field theory to write down a non-perturbative answer, DG, right?
Right.
We have no such thing for string theory. So it's, to answer your question, it should include non-perturbative effects like wormholes, right? We don't have a formalism to answer that in this correspondence.
But if the wormhole is very big, it has
No, I understand. It's an issue, but it's not. And therefore, I'm also, doesn't that make you suspicious of trying to write this, try to get to a definition of this thing, either by holography or by any other means, contours?
Well,
thinking of it as DG instead of D psi over the string.
Right. So if this is not going to make sense, I mean, as you're saying, we need some other way, maybe string field theory, maybe string something, to sort of answer these questions about which saddle points are included. Is there some restriction? And it should be derived. It should be an approximation to something, and we should know what it is
maybe
we're approximating.
There's a long-standing question in string theory. How can we formulate string theory non-perturbatively?
Right.
That has never been answered. String field theory is an attempt to do so, but still it's only perturbative.
Well, the holography is one way to do it.
The answer to that has often just been holography. Now, I did say, at least for some quantum states, holography is the way of defining string theory non-perturbatively. Right? No issue like wormholes comes in. There's nothing that leads you to suspect that that's wrong, like you just stated for visual understanding.
Well, if holographies are non-perturbative description of string theory, certainly using string theory, we derive the low energy action, we then compute these wormholes. I mean, they seem to be classically. Sure. We don't know how to do it in the full string theory. We don't know how to do it in the full string theory.
So there's no problem.
Well, maybe. Yeah.
Well, no, I mean, there's the problem that Steve talked about in his talk. So the wormholes give you the right answer for some things, and they give you the wrong answer for other things.
Right.
So to really understand it, you have to argue why they're not a reliable computation of the things where they give the wrong answer, but they are reliable for the things that you give the right answer.
Right.
And he had this cartoon for how that should work, which didn't sound crazy to me, but I mean, to be fair, it was a cartoon.
Okay, let me move on. I told Douglas I would stop at 2:15 so he can speak.
Sorry, too much.
Oh, okay.
I'm enjoying this. So.
I only have one.
Steve asked, or someone before you discussed what is a quantum black hole, what is quantum space-time?
Right.
And holography, interpreted as string theory, doesn't answer that question. So what is your answer to what is quantum space-time?
Well, in some sense, all this bulk reconstruction is an attempt to get at it. I mean, if we start with holography, which is our best understood framework, we have a quantum theory. We want to find the space-time in some limit, in some approximation. And so these ideas of bulk reconstruction is, I think, our best guess at the moment.
It's approximate quantum error correction.
Thank you. Okay, one more question, and then I'll see the floor to Douglas. And the last question I wanted to bring up is, what is the role of zero metrics in quantum gravity? So this first came up in the early days of topological field theory, when it was Witten who pointed out that 2 + 1 gravity can be written as a Chern-Simons theory. So you can write 2 + 1 gravity in some standard Chern-Simons type form, and A includes the information about the metric, the triad, and A equal to 0 is a perfectly good solution, and it describes a space with no metric. This can be thought of as a space, as a state of unbroken diffeomorphism invariance. You might think of it as the preferred state of quantum gravity, and everything else is some excitation of it or some breaking of the diffeomorphism symmetry. Now, in any dimension, in particular in 4 dimensions, you can write general relativity in first order form, where again, if you introduce a tetrad and a Lorentz connection, think of the tetrad and connection as independent, this is a perfectly good action for general relativity. It only involves the tetrads, 4 orthonormal vectors, 4 vectors or linearly independent, which you define to be orthonormal, and that gives you the metric. And there's no inverse metric. Okay, so once again, in this formulation of gravity, and you can extend this to any higher dimensions, there are smooth solutions with this tetrad equal to 0. So this is a solution. Okay. And in fact, there's this whole family of topological field theories called BF theories, where you just integrate. Okay, so F is some curvature of some connection. If you take a Lorentz connection, this is just the Riemann curvature, 2 form. And B is some form with enough indices so that you can integrate this over the manifold. So this is a topological theory. You can quantize it trivially. And yet, by adding a simple quadratic constraint on B, you can demand that B be expressible as the wedge product of 2 objects like this, and the theory reduces to general relativity. So there are simple topological theories that become general relativity after you add some simple constraint. So what should we make of this? I don't have an answer, of course, but there are a couple. Oh, this can also be viewed as an example of emergent time. Holography is always quoted as giving us emergent space, but this might be a way of thinking about time emerging. If we had a theory in which there could be no metric, and then the metric emerges as something.
This is related to your first 2 questions, or is it just a completely different question?
Is what?
Is 3 a completely different question from 1 and 2, or do you see a relation between them that's caused you to present it?
This certainly doesn't have anything to do with black holes. I'm asking about this more generally in quantum gravity. And I'm also thinking of this independent of any Euclidean functional integral or path integral over metrics.
Couldn't G mu nu equal to 0 be an example of a singularity?
Well, what I'm saying is that there are formulations of gravity in which there are perfectly smooth solutions everywhere where the metric is 0. So it's not necessarily a singularity. And let me just, well, I guess I have a little bit of room. I can just, if people can see over here, I'll just give a couple more examples where this idea of a 0 metric has come up. So the examples I want to mention is, of course, so here, there was Witten's bubble of nothing. So Witten pointed out that the standard Kaluza-Klein vacuum, nothing. So the standard Kaluza-Klein vacuum is unstable. There's a gravitational instanton which nucleates a hole in space. And so the picture is you have 3-dimensional space, you cut a hole in it, but above each point there's a circle in Kaluza-Klein theory, and the circle just pinches off smoothly at this boundary of the hole. So the space has no inner boundary. It's completely geodesically complete, but there's literally no space inside here. Space-time only exists outside, and Witten showed that under evolution this bubble actually expands out. It's like a decay of a false vacuum, but in gravity the true vacuum is nothing. Literally nothing. Another example, which I find very interesting, is Eva.
What are the rules of the game? That says there's no set of points in this space. Or why is G mu 0? When you were talking about G mu 0, I thought you had some set manifold which is just a set of points, and no metric is 0 on it. Or do you mean there's actually no point set?
True, but I'm not sure that the semi-classical approximation can tell the difference. I'm not sure, since this was derived using a semi-classical argument, I'm not sure you would know the difference between this description and the other description.
But here you have a four manifold, and the part where you have a four manifold, you actually have a metric. It's just that there is an interior which is not part of the four manifold.
Yeah, so this is only applicable to the interior. Obviously, this is not a G equals 0 state everywhere. It's a G equals 0 state inside the bubble.
I was imagining you had some kind of continuous manifold where the metric was 0. You're saying that
Well, that was another possibility. This example implements this idea only in a limited region. It doesn't implement
I
it.
agree with these people. I don't see how it implements the idea at all. Unless you can rewrite the bubble of nothing in terms of a metric that is degenerate in certain places, which you have not shown.
Okay, let me give you an example you're going to like better. Okay, and the example you're going to like better is due to Eva. And what Eva showed is that if you take a space-time, suppose we have a compact direction in which the circle is some size bigger than the string scale at infinity and shrinks down to some size less than the string scale in some region in here. Now, it's been known since the early days of string theory that winding modes of strings, if you impose boundary conditions on fermions, so they're anti-periodic and you break supersymmetry, winding modes of strings become tachyonic when their length becomes less than the string scale. And what Eva showed is that the outcome of that tachyonic instability is that all modes of the string become very massive very fast. So essentially, you lose the space-time. And what you end up with is a picture where the conventional space-time looks like this. You can think of the circle capping off. But inside here, you have a tachyon condensate, or you can think of it as some tachyon condensate. So in some sense, there is still points here. There is something, but there's no metric. The graviton has become very massive along with everything else. There's no metric that we can recognize, and what lives here is just some tachyon condensate. And so this could be viewed as a creation of some zero metric region.
Sorry. This semi-positive region outside the tachyon condensate, to what extent is that actually justified as a result of this tachyon condensation?
So Eva and collaborators calculated what happens if you send a signal in. To this thing when the tachyon condenses. And what they find is that signal comes back out. Right? I mean, so it looks like it's just propagating off some space which is kept off like this. Yes, in the back?
Sorry, and what will happen with matter in the presence of a tetrad which is 0 or trying to approach tetrad equals 0? There is always external fields and the fluctuations, unavoidably. They will be probably greatly enhanced.
Presumably, the state would have zero matter as well as zero metric, if this is going to make sense.
The quantum fluctuations of matter, for sure.
Well, but the fluctuations are governed by the metric. Usually, quantum fluctuations are, if you don't have a metric, what do we mean by the quantum?
But zero lengths would imply infinite fluctuations, right? Of matter.
Maybe phi and phi dot commute when the metric is 0. I don't know.
Yeah, Steve.
I just wanted to point out there was this question of whether there's a connection with 2, with the Euclidean functional integral.
Yeah.
And it comes back to this question of the relationship to the Lorentzian functional integral. And so if you try to interpret some of the things, like wormholes or tunneling from nothing, in terms of a Lorentzian contour, you often run into things like degenerate metrics, which is sort of another related, well, it's quite similar to this, where you have zero metric, maybe just some of the eigenvalues of the metric. So in some sense, you have to say what you do with those if you want to connect to the Lorentzian story with the topology change or tunneling from nothing, etc.
Eva?
Well, I mean, I think that question is what the string theory example is particularly useful for, because it's giving a Lorentzian evolution that leads to topology change in a simpler way than the one that is inferred from the Euclidean instanton of Witten, but the outcome is the same in that case. So one of them dominates putatively at large radius, the Witten bubble does, whereas the stringy effect dominates at smaller radius. And the stringy effect is computable, like in string theory, because it's a perturbative string theory question here. The target space can be Lorentzian signature, even though the world sheet signature is Euclidean, as in the textbook analysis. So, yeah. So in this case, we thought of it as a more direct Lorentzian topology changing analysis, rather than having to infer anything from the Euclidean path integral.
But you wouldn't interpret this as zero metric.
Well, okay, so as Gary says, so the reason you would guess that it acts like it's mousing everything up is because of the first quantized world sheet action, in which this tachyon appears where the mass term would appear. And then you do these calculations, and it behaves just like it should under that interpretation. There's particle production that matches what it would for an exponentially growing mass, and so on. So, sorry, what was this precise question again?
Whether you're interpreting this as an example
of zero metric, right? So you could ask, is it a mass or a perturbation around something or around nothing? And what Gary's saying is, there's no ordinary space-time there, and he's describing that as g equals 0.
That's not the same.
Initially, it's a perturbation around what you started from, just like we always do in string theory, right?
But it evolves. And so, anyway, this is a natural
To say that g mu equals 0 implies you have a definition of g mu that is still applicable in this tachyon condensate, and you can evaluate it, and it's 0. I'm not sure you've worked through all those steps.
Well, all right. Maybe this should be in quotes, but anyway, the thing is morally, playing a role here. Yes.
When you send a signal from the left, is there some way that this signal propagates through the tachyon condensate to the right, even if there's no metric over there? Because in that case, you would say that the tachyon condensate, that you have a state there, or you have the tachyon condensate, the metric is 0, but still, something active. If not, I don't think that there's much sense of saying that. Are you saying that everything bounces back?
I believe so. That's what you found, right? You don't have any signal coming out the other side when the tachyon condenses.
A signal came out, then you would say that you have something intermediate there, some state, that where the expectation value of the tachyon is whatever, the expectation value of the metric is 0, but there's something in there, right? But if you don't have, if that thing that you have in there doesn't carry any energy, doesn't propagate any signals, in what sense do you have anything there?
Well, in what sense is g equals 0 anything?
Yeah, but
that you maybe you don't want anything
some
there.
sense for what you have there. If that thing that you have there could propagate signals, if it could carry something through.
Hey, Eric, can we rephrase your question as perhaps is there some meaning in quantum gravity to unbroken diffeomorphism invariance?
Good. Yeah, that would be another way of saying it. In terms of symmetries, is there a state of unbroken diffeomorphism invariance? That
Can we regard all the states we know and love as symmetry breaking?
That would be another way to say it.
Well, can you see the diffeomorphism invariance?
No, this is not example.
No, these are not, because it's localized and everything.
I would have thought things becoming massive is more like g mu going to infinity, because it means that if something becomes very massive, it means that it only propagates over very, very short distances. Yeah.
Look, I think I should stop. I'm already over time. I'd like to turn the mic over to Douglas. Let him say some words about problems that maybe we can solve.
Is that how you divided it up?
Yeah, these are unsolvable problems.
I have a small comment about broken diffeomorphism and gauge invariance. So the gauge field always breaks the gauge symmetry, the full gauge symmetry, because it transforms linearly. It's only the global part that does not change, and similar comments might apply to it.
So is it
Yeah, so for ordinary gauge symmetries,
Like 2 plus 1
no, let's say just Young makes it. So we say Q mu equal to 0, but we do a gauge transformation, it takes that to an A mu which is not 0.
But that's not true for G mu, right?
No, that's not true for G mu itself. So but that would be true for the gauge theory version.
Okay, well, I thought that was great. My part is going to be comparatively disappointing. So I'm going to discuss some problems that have a kind of obvious first step. They're not necessarily the most interesting problems or the ones that you would like to solve, but they're problems for which I think there's been some recent progress that makes it possible to identify a first naive thing to do. So I'm going to list them and then maybe discuss 1 or 2 of them. So the first one is related to something that Gary discussed. It's the semi-classical bulk versus quantum expectations. And I might discuss this more in a second. The second one is the S matrix of a black hole unitary in the semi-classical replica wormhole discussion. The replica wormholes or whatever know that the S matrix should be unitary. A third question is, do replica wormholes play some interesting role in de Sitter or cosmology? A fourth question is, these are just sort of I'm not an expert brainstormer, but I tried to do some brainstorming, and this is sort of what I came up with. So they're a little bit random. Is 3D pure gravity an ensemble? And finally, let's say maybe 1D TT bar with a cutoff. With truncation, I guess, is the term. Versus cutoff gravity. Okay, so I think in each of these cases, the writing is pretty bad. This is why I like to write things in advance, but hopefully it's legible. In each of these cases, I think there's a sort of a first step that one could take. And we can discuss any of them. My plan was to talk a little bit about numbers 1 and 2. But I'm actually curious to see if any of you guys want to suggest some other ideas.
Can you say what you mean by number 1?
Yeah, I mean, maybe I will in a moment. But let's see first if somebody wants to propose some other problem. Ideally, it would be a problem where you have an idea for like the first thing to try.
Can I just ask?
Yeah.
Why ask number 4, and what is the obvious first step?
Why ask number 4?
Yeah.
Well, because 3D gravity is kind of a stupid theory of gravity that doesn't seem to have the same interesting constraints from UV completeness as higher dimensional gravity theories. And JT gravity is like that, and it's an ensemble. So you could wonder whether 3D gravity is also an ensemble. That's one reason. Another reason is that like the computations in 3D gravity have given a continuous spectrum.
So I thought Alex Maloney and a bunch of collaborators looked at 3D AES gravity and argued that it only makes sense for a certain cosmological constant, and that they could figure out what the central charge was and argue it had to be like C equals 1/2, so it had to be dual to the Ising model. Is that not the answer to this question? Because There's only one CFT basically at C equals 1/2.
Yeah, I think that
Maybe two.
I have in mind a different definition of 3D gravity where you try to do the path integral in the bulk.
Well,
that
he
wasn't
also
exactly
was
what they
looking
were
at the
doing.
path integral, and that's doing some magic that I don't understand.
I think they were trying to make a modular invariant torus partition function.
Yeah.
Whereas if you just do it in the, somehow starting in the bulk, then...
They had a specific version of the path integral, which means you find all classical solutions and compute loop corrections on top of those. In JT gravity, we've learned it's very important now to include off-shell contributions to the path integral where there is no solution with that topology. The same
So you're
thing.
saying they just calculated it wrong, or?
I'm saying
they
they
didn't do
missed
the exact,
saddle
they didn't do
points.
the exact bulk path integral.
Well, it was clear that they missed saddle points.
Yes.
You
well, not saddle points. They missed.
No, it's clear they also missed. Well, there's saddle point that they. Well, it's not like they necessarily missed. They know they're there. Just decide to not include them. But even in the case of the torus boundary, there's the Euclidean zero mass DZ black hole, which is modular invariant by itself, and that should give a divergent contribution to the partition function. And if you include that, you get something that looks like Liouville. And that might lead you to claim that the 3D pure gravity is due to Liouville, even though I don't know any evidence to support that at level of genus 2 partition functions. It actually would be quite spectacular if that's true. Then there are, of course, people who suggest that Liouville, in fact, could itself be thought of as ensemble of state.
The tempting first step that one could imagine, first step that I find tempting here is to try to compute the wormhole contribution to two torus partition functions in 3D gravity. And it sounds like that's something that could potentially give a finite and interesting answer that might shed some light on this question.
Sorry, which wormhole geometry are you thinking of?
So there's no classical solution, but you take the boundary as two tori, and then there's something with the topology of an interval times a torus, and you would try to do the path integral on that topology.
Aren't there classical solutions when the boundary has a negative curvature?
There are, but
Even more?
yeah, those are interesting, but they don't have the same interpretation as like thermal partition function on the boundary.
I mean, I thought the problem with trying to do this, and maybe Henry can correct me, is that we kind of don't understand three manifolds as well as we understand.
Yeah, that's going to be a huge problem.
Yeah.
But I wonder whether so there's an obvious first step, and then there's an impossible morass of complications. So.
What is it that you want to know about the manifolds? What's the bottleneck there?
Want to know how to sum over them?
You want to sum over all of them, right?
You can't even classify them.
What?
Yeah, Veronica.
Is the problems means that supposed to mean a question, or is it that there's a problem about the obvious first step?
Oh, sorry. No, some question, some. Yeah, probably most of the first steps are problematic. That's the way it works in first steps. Yeah, Ahmed.
The replica wormhole story, but in Lorentzian spacetime.
Okay. What do you mean by that exactly?
As in, do something analogous to what Mukund and she and Altor did in proving HRT, where they worked purely in Lorentzian space using some sort of linear Kelvich using the bulk.
Do you mean a finite Renyi index or?
Yeah, I mean, do the whole procedure. The finite Renyi index and take n equals to 1. Just reproduce the same results that we did using the same results that we got from the Euclidean computation of Euclidean wormholes.
Let's see how that's a different. Okay, I'm not going to.
It seems to work, right?
Yeah.
I guess it's going to work, but it just hasn't been worked out.
I think there is an interesting problem to try to find the finite Renyi index solutions. Might be related to this problem. Okay, but anybody else want to propose another idea or topic?
I would just add some substructure to 5, but maybe that's.
What substructure do you want to add?
So depends what theory you're talking about in that dimensionality, but you might have bulk matter and you might want to make it local, and then you need to add more. You might want to add lambda 1. You might want to do all these cases.
I was thinking of the thing I was thinking here is the simplest case I could think of, which is to start with JT gravity, which is a matrix ensemble,
apply the TT bar formula for energies with the cutoff to the matrix ensemble, and then study JT gravity with a finite cutoff and ask if they're the same.
And truncate to real energy levels, that's the truncation, right.
Yeah.
That's a great question. One might also want to use 1D, 2D for all this discussion of local bulk matter, and using the fact that the 1D version of that is much better defined. So that's
but it's still more complicated than this thing.
Sure, yeah. But I'm not sure this. So this one just doesn't have any bulk matter.
Right, but there's still a totally sharp prediction.
Yeah.
And well, it's wrong or it's right. I don't know. We could probably try to calculate it. Let's see.
No, I wasn't trying to erase 5. I was just trying to add.
Okay, you want to say also possibly include matter? Daniel, what do you want to say?
Well, I was going to suggest something. It may be contained in number 1. I'm not sure. But I would like to have a better understanding of what we mean by a generic state from the bulk point of view. Like in particular, like when you think about gravity, like it's kind of like not having matter present is like non-generic, right? Like we say usually, like null geodesics should focus. Like they shouldn't like just sit there not focusing because matter should fall through. But then on the other hand, we say that like specifically say at the horizon of a black hole, right? Like you might say, oh, there could be all sorts of things that could be at the horizon of a black hole. Why should there be nothing? That's very atypical. That's one argument you can. On the other hand, you could say, well, whatever you put there, it's going to fall in, and then there won't be anything there. And they're kind of both of those arguments sound reasonable to me.
What is the bulk dual of a random high energy state?
Yeah, for example.
What is bulk? And what's the first step?
Well, you could try to study it classically, right? Like we know that the thermofield double is not generic, so you could try.
Okay.
Putting more.
So let's put matter and then evolve backwards or forwards in time. Now the matter is either on one horizon or the other horizon.
Right, so the problem is like if you put a finite amount of matter, then it always eventually falls in. But somehow for a generic state, we kind of think there should always be kind of stuff around somehow.
But why? Near the horizon? That's...
Maybe.
Okay.
Well, I don't know. This is related to the firewall thing, right? So I don't actually know. But I mean, if there is a firewall, that'll be the explanation probably, is that it's more generic to have stuff there than to not.
I love this question, but I have trouble seeing a first step.
I would think that you want to talk about initial data. I mean, you have some set of initial data satisfying the constraints, and you can ask about, some...
No, but I think Daniel's question is about random states from the perspective of the Hilbert. Full Hilbert
versus boundary. Quantum versus bulk.
Which is going to be a hard question to ask, starting with some initial data.
I mean, the problem is that like the microscopic definition of generic state should somehow be invariant under time evolution, whereas in gravity, like if you try to make up some random, sense of initial data on initial slice, then you evolve, then it all falls in. So it doesn't look time translation invariant. And I wish I understood how to think about that. I don't know. I don't know the answer.
Yeah, Veronica?
In the theme of sort of ensemble versus single theory or something, it would be nice to explore what types of sort of averagings would lead to something looking like gravitational description, let's say. Even if you could get an ensemble, maybe other types of averaging within a single member or other types of distribution would lead to the same thing, and just understanding what is the crucial aspect of that coarse graining or averaging or what have you that looks
okay. Do you want to propose a first step? Or?
Just explore various other types of averaging.
What kinds of averaging do you have in
time
mind?
Averaging,
yeah.
so small intervals, averaging over different initial states, maybe between different eigenstates and some energy band.
I'm not sure.
Okay.
Okay.
Start making that.
Yeah.
Yeah, maybe related to point 2, you can talk about breaking of global symmetry with replicable wormholes. Maybe you can put it.
Breaking global symmetry with what do you mean?
Well, you can try to have a global symmetry theory, and you have super selection rules, and then you look at.
Okay.
Yeah.
Right. Replica wormholes. Okay. Anybody else?
Sort of
feel like there's a sort of reverse or converse question on 7, which is what's the boundary dual of a random thing you put in a bulk? Like the way I have this in mind, suppose I have a wormhole and I replace it with a different geometry, but it's analytic. And then, but it can be sort of any weird thing I make up. Then I can imagine evolving that in Euclidean time, and I could ask the question, do I always get the sort of thing that I would expect from ADS-CFT, where I have like asymptotically ADS boundary conditions, or I get other types of boundaries too? There's a question of whether every bulk geometry I can think of can be approximated well by some pathing. I see you shaking your head. Is that because you think the answer is no, or because you think this is a terrible question? I think the answer probably is no, but it would be interesting to know why it's no, and what sorts of geometries are off limits.
Yeah, somehow thinking about initial data in the bulk seems to be very in tension with thinking about it in the boundary. Seems like, yeah, I don't know. That was the problem I was having too, somehow. It doesn't seem like there's a simple map.
Yeah, one?
In what sense there is a final boundary condition in the theory of black hole?
Okay.
What kind of crazy person would suggest that?
I don't know. Gary, probably.
Okay. Well,
thinking about replica wormholes when the full black hole.
Yeah. Maybe there's a
it's related
comment to point 2, I guess. Maybe maybe unless, well, I'm going to say a couple words about both of these. I'm afraid my comments about this one will be possibly boring and overlapping with previous things that have been discussed, so maybe I'll discuss this one first, and we'll see if we have time for the first part. First thing to try for question 2, so the context is like the replica wormholes know that the entropy of the Hawking radiation should go down, follow the page curve, and it should go to 0. But does it know that the S matrix is unitary? This is maybe in principle a different question. And I think we could consider a model of this that was discussed because evaporating black holes are too hard for a first step. In the paper by Ahmed, Raghu, Wan, and Ying, and also related somewhat to an early paper by Polchinski and Strominger. So the idea is, let's say that we have a space-time that does this, nucleates off a baby universe, and we have an entangled pair, where one pair falls in and one pair stays outside. This is a model for an evaporating black hole. I'm not sure if this is what they meant. Hopefully I'm not, well, whatever. Sort of a model for this kind of situation here. And we could imagine that we query this qubit here and ask what its state is. So the replica wormholes or the island formula predict that this thing should have entropy 0, but what is the state? And so in discussion a week and a half ago, Juan said that the final state is expected to be a random state. And I think that we can justify that. This is probably what Juan had in mind. I'm not exactly sure. We can justify that by thinking about the following. Let's take a bunch of copies of this diagram where we have some like this with index I1 up. Let's do n copies of this kind of thing. In, and then m copies like I originally drew, J1 up to Jm, and then we can connect these guys in any way we want. There's lots of ways that we can pair them together. And the pairing together will identify the state of the qubits in the closed universe here.
So we're going to get the same result as a whole bunch of possible width contractions, setting these i's to some of the j's. So that's the same thing as an integral over states of I1 psi up to IN psi times psi J1 up to psi Jn. So that the statistics of these states that we get here is the same as for saying that we have a random state for the final state. That's the same thing in this model as saying that we have a random state here. So we just have one copy of this whole setup. We don't need to do all these wormholes. We have one copy of this setup, and we say that there's a random state here. It's a random final state. So in the context of this diagram, that would be like saying that there's a random final state that we put here. And of course, that's closely related to the idea of Horowitz and Maldacena. Yeah, Steve?
So this looks a lot like the question of whether information goes down the wormhole. That's basically what you're asking here, I think.
No.
And, that goes, well, you're shaking your head. Let me finish and then we can come back to that. So that goes back to, these discussions we had decades ago. And in the end, we did construct an argument based on what was called the wormhole calculus, where you showed that, in fact, you had a distribution for coupling constants, in modern language, some kind of random ensemble. So I'm wondering if you're saying something different than that here, or...
I hadn't quite finished what I was going to say, actually, but just that there's a connection between this picture here and like a random final state. That you can replace the wormhole discussion by putting a random final state for the interior partners. That's what seems to happen in this model.
Yeah, I think those are the...
Okay, so... To ask something like this question, is the S matrix unitary? So we can imagine dressing up this model by adding another bit. I should have used another color here, but it's another bit that comes into the wormhole like this. So that's the model for the matter that forms the black hole. And now the same kind of calculation will apply, and we'll find a random state here. So that's like a random final state projection on these qubits there. And that's very similar to the Horowitz-Maldacena proposal, but not exactly the same. So it would say that the S matrix from initial to final is something like random state psi times initial final, where initial final are the states of these bits in the interior, or these bits in the closed universe. And this is not going to be exactly unitary. So it looks like there might be something interesting to discuss. There might be establishing unitarity might not be quite as simple as you might think. So there could be an interesting problem there.
Wait, so in Horowitz-Maldacena, the unitarity of S translated to the unitarity of the evolution from incomers to matter.
Yeah, so in Horowitz-Maldacena, they don't put a random final state here.
They put a specific one. I thought you were saying it's a specific
one.
Well,
it's not just that it's a specific element of the random set. It's that it's a special state that's maximally entangled between these.
Well, yeah, it's a unitary. I mean, the way they... Yeah,
so that's not... a random state doesn't have quite that property. So it's close, but not exactly.
But, I mean, it was basically unitarily evolving the left movers to the right movers or something.
In this language, it's just saying that the projection is onto a state that's maximally entangled between the interior modes and the infalling matter. And actually, that led to a whole bunch of confusions. Like there was a Lloyd-Preskel paper, and it leads to some... Preserving that exact maximal entanglement is a little bit difficult. And if you had said you just take a random final state, that would have been simpler. It just wouldn't have been exactly unitary. So maybe there's something that we can learn about how to simplify the final state proposal.
Didn't they even try to do that in the paper of John and Seth? I vaguely remember they talked about also trying a random state instead of this particular.
And just dealing with the small violation of unitarity.
The small, yeah. I'm pretty sure.
Yeah, maybe they probably commented on it. So I'm sure they knew it. So, yeah.
This random final state is only work here for the I have lots of indices, right?
It'll be close to unitary in that case, yeah.
If it's just one qubit, then it won't be.
Right. Then it's yeah. But with one, the one qubit case I think is somehow the most interesting case. But yeah.
Wasn't there a causality problem with the definite final state projection, and does that persist in this random projection?
I think with the
it had to do with preserving that that maximally entangled structure that Douglas said. So if you replace it in this way, I think it's better. But I mean, it's you don't have that issue. You have the issue. It's not exactly.
Yeah.
But you're still are you still post-selecting or not?
Yeah. You're still post-selecting.
Right?
But I think actually that's one thing that seems kind of nice about this is that you could ask. So we have these replica wormholes, and we interpret
not replicas anymore, right? I mean,
sorry.
I thought replica came when we're counting, computing the entropy, and we need all these.
Right. I was stepping back a second. Yes, I was stepping back a second and saying that the computation of the entropy relies on replica wormholes, and we can. Well, in this case, we can try to interpret that in the context of an ensemble as. The wormholes in the context of an ensemble, as Steve and Andy and Sydney did. But then you're faced with a kind of a puzzle. Suppose that we have a black hole, and we evaporate it. We do 1 million experiments, and we find every time it ends up in the same state. So now we know what the state is. So we've now collapsed the alpha state, and we know what the state is, and so there can no longer be any funny business with ensembles. And then we ask, in that theory, we do the experiment one more time with the black hole. How does it evade the firewall paradox? And the way it evades the firewall paradox is the Horowitz-Maldacena mechanism. So we're going to have this thing. We don't need the incoming bit for this. We need this particle to end up in a particular final state, which is the one that the black hole evaporated into 1 billion times before. And the way it happens is that those other experiments that we did will have these wormholes hanging around, where this is in some particular final state chi. And this thing can connect to that. And it effectively puts the final state chi inside the black hole. And it doesn't destroy the entanglement at the horizon by the Horowitz-Maldacena mechanism.
So Ted was asking about causality. If we have a specific but random final state, in addition to it not being exactly unitary, won't it in general be the case that the early Hawking radiation carries out information that hasn't even fallen into the black hole yet, that's going to fall into the black hole in the future?
Relatively, I think this is presented as if the wormholes or the final state projection is happening entirely in the interior of the black hole, but it's not clear that to get to a single alpha state without baby universes in an ensemble, you need to, in the old Coleman and Co. story, integrate out the Euclidean wormholes, integrate out the baby universes, and this induces local operators. Here, the wormholes are the size of the whole black hole, so you have very non-local operators, and those operators need not be supported only in the black hole interior. So an important open question is to what extent are these wormholes causally accessible to the outside. So a naive argument about the location of the quantum extremal surface and how large the quantum fluctuations of that location are tells you that sort of half the time that it will actually extend outside the horizon by some distance. But yeah, maybe that's a.
Do you want to put another question? How should I phrase it?
Maybe it's 10b.
10b. What do you want me to put? How far? How?
Yeah, it's the.
How far out is the band?
Yeah. How? More generally, what is the single shot description of replica wormholes, or what does the description look like once you're in an alpha state?
Okay. And you say it's naive to say that it looks like Horowitz-Maldacena because it could be visible from outside the black hole for some reason? Or?
Yeah.
Let me let Ahmed go because he was sitting there.
This is quick. Do you think the final state idea says that there's a dictionary between Hawking radiation and the inside?
I'm not sure I understood the question. I'm also not sure I'm the right person to answer it, but you want to rephrase it?
Well, I mean, in the replica wormhole story, using the PETS map, we know that there's a dictionary between the Hawking radiation and the inside of the black hole.
Oh, I see.
But is that also guaranteed by the final state, or is it?
I think so. I think you can follow the state back through the Hawking radiation to the interior modes, and then back through the interior modes through the projection to the infalling matter. So depending whether you want the interior modes or the infalling matter, you can get either, I guess.
This is related to 10b, right? This question. The alpha state would be the state with the projection.
Mm-hmm.
Just for saying, okay, you can still build an interior out of this projection. The projector is complex, and then you could build an interior similar to what you boundary conditions.
So put differently, as long as the alpha eigenstate approximation, or this whole alpha story is a good approximation, if you're in an alpha eigenstate, then you're supposed to just have unitary evolution there with one single set of coupling constants. Then you're basically back to the old problem, what makes black hole evolution unitary, and all the solutions that people have enumerated could be enumerated once again, final state, or some non-local interactions, or what have you.
Yeah, I think it's interesting though.
To that situation. Now, maybe there are some new ideas, for example, because maybe there is some larger scale effective operators that are relevant, that are implied because of some connection to the replica wormhole story or general topology change.
But here there's supposed to be a computation, right?
Right.
The final state before is just something you make up, but here if you get it out of something.
Right, and the theory wouldn't tell you what the gravity theory wouldn't tell you what the final state is, but it would say that if you've done the experiment many, many times in the past, then you know what the final state is based on all of the previous outcomes. Maybe, well, I feel okay. I will, instead of saying point 1, I will just say the emotional part of point 1. That I feel somehow like gravity has swindled us a little bit. Like the semi-classical computation in the bulk knows that the entropy goes down. It knows about the page curve, but it doesn't know about what the state is of the Hawking radiation. And normally in quantum mechanics, you compute the entropy, you compute the state, you do your whatever quantum mechanics, and you compute the entropy. And gravity somehow gives you the answer, but it doesn't give you the intermediate step. And I feel that, I personally feel a little bit disappointed in that. But hopefully this is just because we're missing something. Like our this effective theory with the replica wormholes is missing some important aspect of the bulk that will put back the final state. But I don't have any good ideas for that. So okay, maybe we should stop now, and I'll take a picture of these things, and if people have other ideas, it'd be great if we could get some kind of like working groups going or something to discuss whatever ideas people like. But I'm done.